Okay, good morning. Today, for Algebra 2, I'm going to be looking at Chapter 11-2 on probability. So a couple things. Let's talk about the definitions of probability. There's really two different kinds of probability. There's theoretical and there's experimental. So theoretical, is really what it should be on paper, is the way I think of it. And experimental is what happens in the real world. Like if I was to go and say, I had a regular standard number cube with 6 sides, and I asked what's the probability of rolling it and getting a 6. Your chances are 1 out of 6 for that, okay? And that would be the theoretical probability. Now, if I go and take an actual number cube and roll it, 6 times, that may not happen 1 out of 6 times, just because of chances of luck. I might get it 2 out of 6. I might roll it 6 times and not get a 6 at all. So whatever I end up rolling, however many times I actually roll it, will be my experimental probability. So maybe I get 0 out of 6, and that could be my probability. It would be 0%. I rolled it 6 times, I didn't get a 6. That's 0. Or maybe it was 2 out of 6, which would be 1 out of 3, or 33%. So that's the other thing, is just say probability can be shown as a decimal or as percent. So, if I came up with something that's 0.25, that could be, 1 out of 4. I should say, or fraction, which is okay too, right? Which would be 1 out of 4, which is 0.25 or 25%. Any of those really is fine, okay? Usually I'm going with decimal or percent, because usually they're more complicated numbers, and we punch them into calculators, which gives us decimals. So that's why I didn't have the fraction written there. Okay, so first one. Over 60 vehicles are in a parking lot today. 15 are pickup trucks. What is the experimental probability that a vehicle that should be in the parking lot is a pickup truck? In the lot is a pickup truck. All right, so experimental probability, number of pickups over the number of vehicles, okay? Which means the number of pickups would be 15. Up early. So one of the things can be tricky with this is just the simple notation. That P of hit means what's the probability of getting a hit. If I was up here in this other problem and I see that they're asking for the probability of a pickup truck, P of pickup truck, that's what they're asking, okay? So you'll see that notation in a lot of books, which isn't that complicated, just you got to know what they're asking for. So that's why I'm writing that down. All right, so back to this one here. So probability is the number of favorable outcomes over the total number of outcomes, which means the favorable outcomes would be getting a hit. The total number of possible outcomes, well, she was at bat 50 times and got 20 hits, so that's 20 out of 50, okay? Now you're making a prediction based on that, which means if I take my calculator and go 20 divided by 50, I get 0.4. Or if I multiply that by 100, I get 40%, which is also 2 out of 5 as a ratio, but usually, like I said, we're usually using decimals and percentages. All right, so that's that. Number 3, what's the theoretical probability of rolling a 5 on a standard number cube? So a standard number cube has 6 sides. You kind of have to know that, which I think you've probably seen in most of the board games you played as kids and stuff, or as adults. What is the probability? Well, once again, it's the favorable outcomes over the total number of outcomes. So the favorable outcome would be rolling a 5, and there is 1 5 on a number cube. There are 6 sides, which gives me 1 out of 6. And if I write that as a decimal, I get 0.16 repeating. or if I multiply by 100, I get 16.7% approximately, okay? If I round off slightly there. All right, so that's your chances. Yeah, good. This one, a little different. What are the chances of getting a sum of 5 on a roll of 2 standard number cubes? All right, so you got to know a couple things here. You need to know that there are 36 possibilities for 2 number cubes, 1 through 6 times 1 through 6. It's actually in the next section we do about compounding 2 events happening at the same time, but you end up multiplying those things. So that's how I got 36, which is like 6 times 6. And then you have to figure out how many combinations will add up to 5. Well, either you get a 1 and a 4, or maybe I get it the other way around, right? Which also counts, 4 and a 1. Or I get a 2 and a 3, or a 3 and a 2. Either way, that's 4 possibilities, okay? Which means my chances of getting, there are 4 favorable outcomes over 36 possible outcomes, okay? And if I divide that out in my calculator, I get 0.1 repeating. Instead of doing it that way, let's go like this. 0.1 repeating, 0.11. And if I multiply that by 100, I get 11.1%. That is repeating. You can put the bar over it. At some point, usually you round off, okay? And those are your answers, okay? All right. This is the hardest part of this whole lesson here. Is this, if you can do probability with combinations, and this is the way it works. It's kind of neat. It's if anybody likes playing cards, this is the section to figure out. It says this: what is the probability of being dealt exactly 2 sevens in a 5-card hand in a standard 52 card deck? So we're going to use combinations. Remember the combinations formula? I'll write it down for you. But combinations where order doesn't matter, which is this situation, because cards. It doesn't matter. I don't care if I get the 7 first or second. Order doesn't matter. So this is the formula for combinations, okay? If you need to review this, I'd suggest going back to the last section, 11-1, and going over that on combinations and permutations. Anyway, I'm doing it in my calculator mostly here. I will show you how to come up with the numbers and stuff here, though. But since order doesn't matter, we're using combinations. So the first thing I'm going to figure out is what are the number of combinations of 2 sevens out of the 4 sevens in the deck, okay, which is 4 and 2. And a quick reminder, the bigger number always goes on the left over here in front of the C, and the smaller number goes on the right of the C. So that's the first part. The second thing I'm going to figure out is the number of combinations of 3 non-sevens from the other 48 cards, right? I've already taken out the sevens, so there is 4 sevens. There are 52 cards in a deck. I took out 4. That leaves 48 cards for the other 3, which gives me C48 4 3 C48 C3. There was a typo there. I fixed it because there was only 3 cards left. That's why it's the 3. So it's the 3 and the 48. Those give me my 2 numbers on the C. So if I'm looking for the number of 5-card hands with 2 sevens, I multiply those 2 things together. Okay, the 4C2 and the 48C3. I'm multiplying these 2 together, and that will be the numerator. The denominator is going to be the total number of possibilities for 5-card hands, which is 52C5, okay? Which means I did all that, and I'm just pulling that together. And this is the big thing that I came up with. The 4C2 times 48C3. Divide that by the total number of possibilities, which is, 52 C3, another typo, that should have been a 5 over here. All I did was take these three things here and put them into a fraction. And I just wrote it down wrong. It should have been with a 5. The 2.5 million is still correct. So I get 103,776 when you take your calculator and go 4 combination 2 and 48 combination 3. Multiply those things together. The denominator, if you take a calculator and go 52 combination 5, you get 2.5 million. And you divide them out and you get 0.0399, which rounds off to about 4%. If I multiply by 100 to get you get 3.99, and we round it off to 4. So that's the answer, is about 4%. So, next one. That's the setup. This one I'm not writing out all the words. I'm going to break it up piece by piece. What's the probability of being dealt 4 sevens in a 5-card hand? 4 of a kind, right? For anybody who's a poker player out there. So I want all 4 sevens. So there's 4 sevens in the deck, and I want all 4. That gives me my 4C4. Okay. Next, I'm going to figure out, there's only one other card, right? I'm getting 5 cards. 4 of them are sevens. That leaves one other card. So that's where the 1 comes from here. And if I took the 52 cards and I subtracted out the 4 sevens, that's 48 left. So that's my 1, 48 are my 2 numbers for the combination. The last number is the same, is always the same if you're looking at all the cards in a deck. I'm using 5 cards out of 52. So that's 5 and 52 are my 2 numbers. And now I multiply those together and divide by the 52 and 5. And I get 48 over the same denominator I had in the last problem, which was 2.5 million. Okay. And if I divide that out, I get 0.0019%. So that's like 2 out of 1,000, or 1 out of 500. Really small chances, right? If you deal it out 500 times, it happens on average once. So chances of getting 4 sevens on a 5-card deal are slim. Okay, so that's that problem. Those are pretty neat, and some real-world applications there. Next, we're going to talk about geometric probability with geometry, right? So this has like shapes in it. I took a picture of this one, just so you can kind of see what it was talking about, what we were talking about. A batter's strike zone depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random within the batter's strike zone, as shown in the figure below, has a high inside strike, one of the hardest pitches to hit? So if you see here, I've got what's important is I got 2 rectangles, okay, and I'm trying to hit the red zone. So I'm looking at the area of the big rectangle and the area of that red rectangle, okay, and you can see the numbers. I rewrote it over here actually. So, once again, it's that probability in its most basic form is favorable outcomes over possible outcomes. So the favorable outcomes would be what happens when you get a strike in that area, and the total possibilities it's the rest of the strike zone. We didn't talk about if you missed the strike zone, they just assume that he's putting it in there. So the area of the red, the area of the high inside strike zone is, remember, area is length times width for a rectangle, which is the 6 times 4. The denominator is the 17 times 22. So if I multiply those out, you multiply your 4 and the 6, you get 24, multiply 17, 22, divide it, and you'll get 0.064 or 6.4% if I multiply by 100 or move that decimal point 2 to the right. Okay, so there's your possibilities. Next one. I want you to try this one. It's the same problem. The only thing that's different is we changed the sizes of the strike zone and the high strike zone, the high inside strike zone. So I want you to try this out. Draw a diagram and then do your ratios. I want you to hit pause and then come back. Hit pause now. Great. Welcome back. So if you did this correctly, you should have gotten that. All right, so there's what the answer should have been. All right, next. So these are there's several problems like this that you'll see in your work. So remember the P of blue down here means what's the probability of getting blue. Let me read the problem first though. It says you have a bag full of marbles. There are 25 red, 10 blue, and 15 green marbles in the bag. So what's my probability of getting a blue? So once again, that's, favorable over the total, something like that, right? Favorable would be if I get the blue, right? There are 10 blue, and the total number is, let's see, I got 25 plus 10 and 15. So if I add all those up, I get 35, 50. So 10 out of 50, which is 0.20 or 20%. What's my probability of getting a red? So this time I've still got 50 marbles in the bag, right? But there are 25 red, which gives me 0.5, or remember, it's not 5%, is 50%. You move it 2 units to the decimal 2 to the right. And the last one, what's the probability of getting a blue or a red? So there are still 50 marbles in the bag, so that part doesn't change. However, blue or red, let's see, 25 red and 10 blue, which means it could be either, which means I'm going to add those two things together, okay? The 25 and the 10, and I will get 35 over 50. And if I punch that into my calculator, I get 0.7 or 70%. Okay? And those are my answers. And I believe, yep, that was my last problem for today. So if you have any questions, please bring them to class, and have a wonderful evening.